Hi everyone, I'm from the VIPL group at the Institution of Computing Technology, Chinese Academy of Science. We will be presenting our work titled Intrinsic Imaging Model Enhanced Contrastive Face Representation Learning. Recent years, deep learning methods have achieved great success in several face analysis tasks. However, this success largely relies on training on large-scale labeled face images, and we need to train different models from scratch for each downstream task. Therefore, it's worth exploring how to use the large-scale unlabeled data to learn general representation of different downstream tasks. In detail, we first learn a universal face representation with large-scale unlabeled face images. After that, we can transfer the learned foundation model into different downstream tasks with limited data. Contrastive learning holds the key to most sought self-supervised learning methods. They treat each image as an independent category and can learn transform independent features in a self-supervised manner. Despite the great success, such representations are often suboptimal for specific downstream tasks because they are unaware of the domain-specific prior knowledge. Therefore, researchers have set specific auxiliary tasks for different downstream tasks. In this paper, we propose a 3D-aware contrastive face representation learning method, which enhances the contrastive face representation learning with the physical imaging model. We decompose the input image into 4 intrinsic components. After that, the intrinsic components can be reconstructed to the input image with a differentiable render. With the introduction of the intrinsic imaging model, the proposed method can obtain a better perception of the physical priors, resulting in better performance in various downstream face analysis tasks. We notice that the 3D intrinsic component decomposition often crashes to a local optimal state. In this case, the model will learn an extreme face pose and restore the input image with the profiles. In addition, we also found that the model fits face depths correctly in the earlier training phase, but falls into the local optimal solutions as the training epoch increases. Therefore, we introduce a model-consistent regularization to supervise the depth prediction weakly. The EMA result of the online decoder is used to estimate a stable depth result to regularize the online model. To evaluate the effectiveness of introducing the intrinsic imaging prior, we perform unsupervised pre-training on the syllabi and web face datasets. Syllabi is a popular face attribute dataset. We use the training set of 162,000 images for self-supervised pre-training. Web face is a new face recognition benchmark, which includes 42 million images of 2 million people. Due to its problem of uneven image quality, we cleaned the dataset to 20 million images based on the SSD FIQA method. The bottom half of this page shows the result of the image quality assessment and some image example. We first evaluate the proposed 3D CFL in the face attribute estimation task on the LFW attribute dataset. To further evaluate the generation capability under the limited labeled data, we use different percentages of labeled data for training. and show the number of labeled data in the table. We can see that the proposed method outperforms the SOTA supervised pre-training and self-supervised pre-training methods. Meanwhile, the proposed method can even achieve similar or better performance than these supervised methods. We also evaluate the proposed 3D CFL in action unit detection and expression classification tasks. We can notice that the proposed 3D CFL could also achieve a SOTA performance in these downstream tasks. We also found that the improvements between different methods are more pronounced when only a small percentage of label data is available. In addition to the previous results, we further evaluate the impact of different components, different backbones, and different dataset settings on the model's performance. To conclude our talk, we summarize 3 points. Firstly, we found that 3D intrinsic component decomposition and re-rendering can enhance the adaptability of contrastive representation learning methods to face images. Secondly, the model consistency regularization strategy can alleviate the instability problem in the 3D intrinsic component decomposition process. Finally, the experimental results show that universal face representation learned in large-scale unlabeled datasets can be transferred to different downstream tasks with limited data. Thanks for listening, and feel free to ask us questions.